Okay, we are in section 4.5, optimization 2, and I'm going to do problem number 7 on page 323. Minimizing packaging costs. What are the dimensions of a closed rectangular box that has a square cross-section, a capacity of 128 cubic inches, and is constructed using the least amount of material? Okay, so we have a rectangular box with a square end. A square, of course, is a rectangle with all the sides being the same length. So the square end, I'll just let the sides be represented by X. And then the length of the box I will let be represented by Y. Now, the first question you ask in all these problems is what is it that they want you to minimize or to maximize? And they want us to minimize the amount of material used in constructing the box. The box is to have a volume, always to have a volume of 128 cubic inches. But is there a way to build the box such that the amount of material used is a minimum? You know, think of this as a cardboard box. How many square inches of cardboard will I need to make this box? As a matter of fact, what is the least amount of cardboard? So to do that, to minimize the amount of cardboard, that's really equivalent to minimizing the surface area of the box. So let's put that down. I want to minimize the surface area. That's the first thing you ask yourself in these problems. What is it that you want to minimize or maximize? And then you have to build a function. And then use the derivative to find the critical points and find where it has, in this case, a minimum. Now, the surface area of this box, let me come up with at least a beginning or first step in creating this function. Let me come up with a working equation. What is the surface area of this box? First of all, notice that it has square ends. So the front end and the back end, there's two of them. So 2x squared would be the area of the front and the back. And then there are four sides that have the same dimensions. So I'm going to add 4. And what are those dimensions? That would be x, y. So I've got the square ends, and then I got the four other sides going around. So that would be the area. Now, this is a step in the right direction, but I have two variables there. I have the x and a y, and I need this function. I need an area function in terms of just one variable. So typical of these problems, I've got to go find another equation relating the x and the y. And the 128 cubic inch capacity, the volume of the box is 128. So let's come up with a little equation for the volume here. The volume of a rectangular box is just the length times the width times the height. So in our case, it's x times y, or x squared y. And the volume is a constant. So I have a relationship between x and y, or another one. I really have a system of equations here in some sense, and I'm going to use substitution. Probably the easiest way to do that would be to solve for y in terms of x, because then I can take this value and, since it's equal to y, put it in for y, or substitute in for y into the equation. Now I can write area as a function of just one variable. It's 2x squared plus 4x times 128 over x squared. And let's simplify that. A of x is 2x squared. The x cancels with 1x in the denominator, and 4 times 128 is 512. Now, function of one variable. Let's take the derivative. Notice that 512 over x is the same thing as 512 times x to the minus 1. So minus 512 x to the minus 2 would be the derivative. Set the derivative equal to 0. And in this situation, it's a good idea just to bring all the terms together on the right side as one fraction. So I'm going to have to multiply the 4x by x squared over x squared, which would give me 4x cubed over x squared. And then combining the two terms, 4x cubed minus 512 over x squared. So that would be true if the numerator, the 4x cubed minus 512, is 0. And solving for x, add 512 to both sides, divide by 4, and x is the cube root of 128. Okay. Now the cube root of 128 is 5.04. Now does that produce a minimum or a maximum? Let's try the second derivative. If I take the second derivative, I'll get 4 plus, I'm taking the derivative of a prime, I'll get 4 plus 1024 x to the minus 3, or 4 plus 1024 over x cubed. Actually, that'll never equal to 0, so there's really no critical points there. As a matter of fact, the second derivative is going to be positive for all positive x. Second derivative is positive for all positive x that we would even have as possible dimensions of the box. Then that means that this x at 5.04 is going to be a minimum. Okay, now that means the dimensions of the box are 5.04 times the other x, 5.04, times what would be my y value? Well, 128 over x squared is equal to y. So if I put 5.04 and square it and divide it into 128, I get y equal to 5.04. So the answer is I have the best way to build this box is to make it a cube of length 5.04 inches by 5.04 inches by 5.04 inches. It will hold 128 cubic inches, and the area will be a minimum, and therefore it will take the least amount of cardboard to do it. One other question I could have is, what amount of cardboard will it take? What is the square inches of cardboard it will take? How would I calculate that? To do that, I just need to put the x into my area function. So I'm going to evaluate the area function at 5.04. And I get 152.4 square inches. And oh yes, the dimensions are all in inches, so I should put my inches there on the 5.04. Alrighty.